Hello students, I am Shavika and we are continuing with the chapter Periodic Classification of Elements. After studying Mendeleev's classification, we now move on to the modern periodic table that we use in today's time. So the modern periodic table was given by Henry Moseley in 1913. He showed that atomic number of element is more fundamental property than atomic mass. Atomic number, it determines the number of electrons in the outermost shell, and that is why he said that it is a more fundamental property of an element as compared to atomic mass, which is the sum of the number of protons and the number of neutrons inside the nucleus of an element. So let's, for review's sake, I'll just tell you that atomic number is the number of protons and atomic mass is the number of protons plus neutrons. So he said that because number of protons determine the number of electrons, it was a more important property, and he based his classification on atomic number instead of atomic mass, which was being used by people up until now. It was because of the development in science that we came to know that atomic number is a more relevant factor, and that is why Henry Moseley decided to base a classification on it. So the modern periodic law stated that properties of elements are periodic function of the atomic number. Now, atomic number here is the change from the law given by Mendeleev. He talked of atomic mass, but here we are saying that they're a periodic function of their atomic number. Atomic number again being the number of protons present inside the nucleus of an element. Based on this, he gave this modern periodic table, which looks something like this. It has groups. There are 18 groups, and it also has periods. So you see that this arrangement is done in a specific way to put metals together, non-metals together, and we'll study more about this arrangement. So let's move on. Now this has 18 groups, which are the vertical columns, as you can see. 1, 2, 3, 4, 5, 6, and up until 18, it has 18 groups. It has 7 periods, which are the horizontal rows. So it has 1, 2, 3, 4, 5, 6, and 7. There are 7 periods, which are vertical rows. And now we will understand what is the basis for which elements are put in a group and put in a period. So when we understand this, we'll be able to understand what is the basis of this entire classification. Now, elements with same electrons in the outermost shell or the same valency were put together in the same group. Let's take the first group. So I'll just show you the first group. This is the first group: hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. So I'm taking the first few elements from here. When we take hydrogen, lithium, sodium, and potassium and study their electronic configuration. Now, hydrogen, of course, has 1, so it's a simple configuration. It has 1 electron in the K shell. When we talk about lithium, it has atomic configuration of 3, which means it has 2 electrons in the K shell and 1 electron in the L shell. Then we move on to sodium. So it has K shell, L shell, and M shell. Atomic number 11, so 2, 8, 2 plus 8, 10, and then 1. Potassium, atomic number 19, K, L, M, N, 2, 8, 8, 1. You add them and it's 19. So you see, this is the kind of electronic configuration of all the elements in group 1. Now you see, what is the common pattern here? They all have 1 electron in their outermost shell, right? So the electronic configuration of the element will show us that when show us the number of valence electrons, and you see that in a group, in any group that you take, the valence electrons will be same. The number of valence electrons will be same. So in the group 1, we have taken from hydrogen up until potassium. Even if you go further, you'll see that there's only 1 electron in the outermost shell in the group 1, and that is the basis for classification. Now, if you are unfamiliar with how this classification works, I will just remind you. Now, the number of electrons in the outermost shell depends on the 2n square rule. So, for the first shell, the n is 1, and so for the K shell, the maximum valency would be 2. After, when it gets 2 electrons, it's stable. Then it moves on to the next shell. For L, if we put 2 here, it would become 8. Again, so 2 2s are 4 and 4 2s are 8. For M, if we put 3 here, 3 squares 9 and 9 2s are 18. So it goes on increasing like that, and that is the electronic configuration, and that is why when one shell is full, electrons move to the next shell and so on. This is how it works. Okay, so now that you've understood how elements are put into different groups, let's move on to another example and take up group 17. So I'll just show you the group 17. Group 17 is here. It has fluorine, chlorine, bromine, iodine, etc. So I've taken up two elements from the activity, which are fluorine and chlorine. Now fluorine has atomic number 9, which means it has K shell and L shell. K shell has 2 electrons. When you subtract 2, you get 7. Chlorine has again K, L and M shell. It has 2, 8, 7 configuration. So you see that both of them have 7 electrons in the outermost shell. So the number of electrons in the outermost shell of in the group remains the same. Now, what if you're given a reverse question? Now I'm telling you how to find, like how to see that the pattern exists in the group. But what if you're given an element and you're asked to find its group number? So it's very simple. If the element has 1 or 2 electrons in the outermost shell, then that becomes the group number. The group number obviously similarly becomes 1 or 2 respectively. But if it is 3 or more electrons in the outermost shell, then the group number becomes n plus 10. So for example, let's take aluminium. Now aluminium has atomic number 13. When you arrange it, you see that the electronic configuration comes out to be 2, 8, 3. Now it has 3 electrons in the outermost shell. So the atom, because it is 3 and more, we will add 10. So when we add 10 to 3, we see that the group number becomes 13. Now let's go and see if it is in fact in group 13. Group 13, aluminium. You see? So whenever you have to find out the group number of an element, if the first arrange it in the electronic configuration of KLM shells, whatever the number of shells are, after arranging, see what is the number of electrons in the outermost shell. If the number of electrons in the outermost shell is 1 or 2, then the group number becomes 1 or 2 respectively. Let's take sodium for example. So we have 1 electron here in the outermost shell, because I said, as I said, that if it is only 1, then the group also becomes 1, and you know that sodium lies in group 1. If we had taken magnesium, we would get a configuration of 2H2. Because again, even if it's 2, then you still go with the group number 2, so magnesium should be in group 2. So let's see. You see, magnesium is in group number 2. So up until 2, if it's 1 or 2 electrons in the outermost shell, then the group number is the number of valence electrons. But if it becomes 3 or more, then you add 10 to get the group number. Do you understand that? So because it was 3 in aluminium, it was more than 2, we added 10. Again, if it was 14, 15, 16 or any, the number of electrons was anywhere more than 2, then you add 10 to get the group number. Now let's understand the second aspect, which is the periods. So periods are the horizontal rows. They determine the number. They determine the number of shells that elements have. So in a period, the number of shells remains the same, whereas the number of valence electrons is not the same. So let's take the example of period 2. The period 2 has elements of lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. All of them have the same number of shells. I will demonstrate this to you. So lithium has atomic number 3. Beryllium has 4. Boron has 5. Carbon has 6. Nitrogen has 7. Oxygen has 8. Fluorine has 9. And neon has 10. Now, what is the commonality here? The number of electrons in the outermost shell is not same, but the number of shells is same. They all have 2 shells. And that is the basis on which you find out the period number of an electron, of an element. So how do you find the period number of an element is, first you write down its configuration and then you see what are the number of shells here, and the number of shells will determine the period number. Now let me take another example. Let's again take aluminium. Aluminium has atomic number 13. So K, L, M shell, 2, 8, 3. So it should belong to the third period. Let's see. You see, aluminium belongs to the 1, 2, 3, third period of the classification. So for the period, the rule is simple. You first write the configuration. You note the number of shells. The number of shells becomes your period number. So if you're given an element and you're asked its location, you will have to write down its configuration. The valence electrons will tell you what is its group number. If it is 1 or 2, then that becomes a group number. If it is more than 2, then you add 3. Then you add, if it's 3 and more, then you add 10 and it becomes your group number. Whereas for period, you just understand that what is the number of shells that it has, and the number of shells becomes the period number. So that is how you find the location of any element in the modern periodic table. Now the position of hydrogen. So it was a point of discussion in the previous classification as well, that where do you put hydrogen? Do you put it next to alkali metals because it shows similar properties, or do you put it with halogens because it also shows similar properties to them? So it resembles alkali metals because it has one valence electron which it can give to achieve a stability. But it also resembles halogen as it has one electron less than the stable configuration. So it needs 2 electrons, and if it takes one more, then it will get a stable configuration, which is also true for halogens because they have 7 electrons in the outermost shell and they need one more to get a stable octet. But hydrogen, after a lot of review, was placed in group 1, period 1. It was done so because it was the smallest element and it exists more as a cation. So more frequently, it exists in the form of H+, which is similar to that of alkali metals. And it also shows properties, chemical properties similar to alkali metals, and that is why it was kept in group 1, period 1. So that was the final verdict on the position of hydrogen in the modern periodic table.
Now, subscribe to Bright Tutee course at ₹1 per day only. Download Bright Tutee app from Play Store and get the online courses prepared by competent and experienced teachers for different education boards of classes 6 to 10. Bright Tutee courses are available for the subjects of Math, Science, Social Science, English and Hindi in English and Hindi medium. Bright Tutee follows 3-step approach, that is learning, assessment and exam preparation. In learning, topic-wise video lectures with explanation of concepts and discussion of textbook examples and questions are available with the solutions. In assessment, topic-wise online MCQ test, practice assignments and chapter-wise question bank are available with the solutions. In exam preparation, previous year's question papers, sample papers and model test papers are available with the solutions. Sign up today on Bright Tutee and avail your courses at affordable prices.